So first, let's step back and think about what we mean when we say make an algorithm more efficient. We have to think abstractly, meaning we don't care about the machine running our algorithm anymore, whether we wrote it to run on this old Nintendo or on an ENIAC, which is much slower. Both of these computers could run our algorithm. We don't want to think about the machine anymore. What we do want to focus on is two things. We need to understand what we mean by size. What is the size that our algorithm requires? And time. How long it takes to solve a problem. We really need to nail down these two concepts. Now, to do so, I want to convince you that a computer is equivalent to what you could do with a pencil, a large stack of paper, and a very simple calculator. So a modern computer is very similar to this. Instead of paper, it uses digital memory, and it has a central processing unit which contains something called an ALU, which I'll explain in a second, which is its calculator, and it can access a calculator, say, 1 billion times per second, and basically run through very simple steps. And that's all a computer is. There's no magic. So first, let's just make sure we understand size from this abstract perspective of applying to any computer. We have some algorithm which is a series of instructions, and let's say this is in English. Well, what's the steps involved in getting a computer to read this? First, we take our English instructions and we write it in a high-level language, such as JavaScript, which we've already done. Next, after JavaScript, it gets processed into a lower level, which means it kind of gets expanded into more primitive steps using, let's say, assembly language. So I'll give you an example of here. Here is just comments. This is English. But these are the steps the machine's actually running. And here's an example. C JMP is jump, which means, go to a new position. And is a logical operation. These are very, very simple steps. And that's all I want to convince you of. So below assembly is the final step, which is machine code. And here's a nice clear example. Let's go from English to machine code just to convince ourselves. If I say, given b, I want you to subtract 1, you'd say, okay, b equals b minus 1. Okay, that will decrement b. So dec b is assembly for decrement b by 1. And this is the machine translation. So this, when a machine sees this, it knows to decrement b by 1. And I'm telling you all of this just to convince you that when you go from an English description of a program to a machine description, you end up with this, a long string of zeros and ones. So both our algorithm and the input we provide is always measured in bits. And just to give you an example, a modern day hard drive, say, can hold a terabyte of bits, which means on this tiny little box, or inside this box, you can store 8 times 10 to the 12, which is 8 trillion zeros and ones. So if you want to store 1 trillion ones, or 8 trillion ones, you could store 8 trillion ones on this hard drive. Now let's quickly cover time, or you might call speed, how quickly our algorithm executes. And we need to develop a very abstract measure for this because every computer runs at different speeds, as you know. Remember, a computer is reading from some list of very basic instructions, and it has access to a really primitive calculator, which it can use. And it is called the ALU. And the ALU is inside the CPU. And the ALU is the arithmetic and logic unit. So it can do very basic things like add, or it can subtract if you provide it. It can also do very basic logic operations like and or. So the ALU is that tiny calculator that the computer has access to, and think of it as basically answering very simple questions. That's all the little calculator can do. And Here is a instruction set list to give you an example. This is from a microcontroller, but it applies to anything. On the left-hand column here, you'll see add WF. And the description tells us what that operation does. It takes F and D, and it adds W to F. And here is dec F. That's decrement F. So subtract 1 from F. Or move F. That is going to move F into a new location. Now what's most important here is this column, cycles. Notice these operations, these primitive operations, they all take approximately 1 or 2 cycles. Another way of saying this is that all of these operations take a constant amount of time. So they will never hang or repeat over and over and over. You can send any of these instructions and you'll get an answer in 1 cycle. Okay, cycle is not second. Cycle, again, is relative. For example, cycle in the ENIAC, the computer could do 5,000 operations per second. And remember, a computer is powered by a clock, which is basically a toggle going back and forth, back and forth, back and forth. And however fast it can do that toggling, that's how many cycles it can operate on. So a modern computer could do much faster, let's say 10 to the power of 10 per second, or it could even do 1 trillion cycles per second. So now we can summarize. When we talk about time or speed of an algorithm, we are not talking about seconds. We refer to number of primitive steps. We say primitive steps because we assume each primitive step takes a constant amount of time. So simple calculations will take, let's say, one step. But when we have a computer run complex steps, such as our algorithm we wrote, it's going to take many steps, right? There is no tell me if it's prime operation in the computer chip. The computer chip can only do those very simple things like you would do on a piece of paper.